The Internet has had a tremendous impact on our world. Our long-term vision is to build a matching quantum Internet that will operate in parallel to the Internet we have today. So, what is the quantum Internet? Well, it is a network. The nodes will be quantum devices of different computational capabilities. These nodes will be connected via quantum channels, channels that allow the transmission of quantum information. Intermediate nodes called quantum repeaters will be placed between adjacent nodes whenever losses are too large. Finally, via entanglement swapping and teleportation, it will be possible to create virtual channels between nodes that have never interacted. This network will enable the transmission of quantum information between any 2 points on Earth. Building a quantum Internet will be a tremendous challenge. Why would we want to do it, given the success of the Internet we already know? We want to build it because it will be useful. There are many communication tasks for which quantum resources offer a qualitative advantage. Perhaps the most famous of these tasks is key distribution. Suppose that two distant parties want to exchange a secure key, perhaps to perform encryption with it at a later point or for other purposes. Unfortunately, it is not possible to distribute secure keys between distant parties with classical resources, at least unless one is willing to believe that some computational problems are untractable, or that the computational devices of a potential eavesdropper are limited in certain ways. On the other hand, quantum resources allow to distribute secure keys between distant parties. Key distribution is the best known task, but it is not the only one. We know of better protocols for synchronizing clocks or for extending the baselines of telescopes. Quantum thus allows to transmit both classical and quantum information in a completely anonymous way. Quantum also promises advantages for problems in distributed systems. One example is so-called Byzantine agreement. In this task, the objective is to agree in the value of a bit in a coordinated fashion in the presence of a subset of faulty and potentially adversarial nodes. Protocols require a number of communication rounds in order to reach agreement. The number of rounds of the best classical protocols roughly scales linearly with the number of users. However, with quantum resources, it is possible to reach agreement with a constant number of rounds, which is independent of the number of users. There are many other communication tasks, notably in the two-party crypto domain. But perhaps surprisingly, quantum communication also finds application in computation. Suppose that we reach the time when the first powerful quantum computers are built. No matter how the technology evolves, at first, these quantum computers will not be widespread and will be owned by a few actors, universities or perhaps big corporations. A quantum network would allow to transmit a quantum state from a client, perhaps the partial output of a computation, transmitted to the distant server, let the server finish the computation and get back the resulting state. Quantum also allows for the following more sophisticated task. It is possible to perform a computation in a remote server in such a way that the server does not learn anything about the state or about the computation performed. This is called blind quantum computation and requires the client to be connected via a quantum channel to either provide some input state or in other protocols to perform some very simple measurements. These are just some examples of the tasks we know today. Analogous to the classical Internet, we also expect that most applications, and probably the most useful ones, are yet to be discovered. In summary, building a quantum Internet will be a tremendous scientific and engineering challenge. We want to undertake it because we believe it will also be tremendously useful.